Okay, so welcome back. The plan for today is to continue with chapter 6, 6.6, dividing polynomials. So we started this before break, but I want to kind of recap some of the work we did before break. So we'll go back through that maybe a little quicker than we did initially, and then move on to dividing a polynomial by a binomial. And we'll see that, dividing a polynomial by a monomial, whether it's just a number or a variable or number times variable, it all kind of works more or less the same. But once we get to a binomial, things become a little bit trickier. So that's really where we're going to focus our efforts today. I think on the schedule, we also had 6, 7 slated for today, but I think if we can get through dividing polynomials and feel comfortable with that, that'll be a win for today. And then we can just wrap 6, 7 in with the beginning of chapter 7 next class. The quote of the day today is by Thorstein Veblen, an economist from 100 or so years ago. And he said, the outcome of any serious research can only be to make 2 questions grow where only one grew before. So really highlighting the idea that scientific inquiry, I guess in a sense, answers questions, but if we're, as Epictetus might say, one of our previous quotes, if we're not being conceited in our knowledge, we don't want to ever think that we've answered all the questions and we know all there is to know. When we answer one question, we should find 2 more questions that we didn't know about before. So if we're not coming up with more questions, the more we learn, then perhaps we're getting conceited in our knowledge. So that could apply to, cutting edge research. That could also apply to reading through a textbook. And, if you go through, 3 polynomial problems or something, and you say, oh, okay, I know how to do this. Ask yourself, okay, how would this change if, okay, I have a quadratic in the numerator. What if it was a cubic? Would anything change? I have a binomial in the denominator. I have a linear in the denominator. What if one of those characteristics changed, right? So we could always, when we learn a little bit more, we could always come up with more sophisticated questions to ask. And I think that's a really good way to engage with material, especially in math, where things are so kind of rigidly defined. We can ask such questions very carefully and precisely, but also in other fields, right? You're in biology or something, and it's, oh, your instructor told you about this cool, organelle in the cell or something, and you ask, wait, well, why does the cell need that to do that, right? Why waste the energy making this organelle to do this thing, or what would happen if it wasn't there, or does that cause a certain disease that you might be able to look up? So you can always engage with the material a little bit more by going a little bit outside of what you know, asking the next couple of questions, and then trying to find an answer to them. So okay, so we will start into 6.6. And again, we covered these exact problems before spring break, but because that was about a week and a half ago now, let's just go back through them. So just to review what we had done before. And we talked about dividing, sorry if my throat's a little cruddy today. My allergies are acting up with springtime coming around and all my neighbors mowing their grass for the first time and everything. So we talked about dividing a polynomial by a monomial. And we said, okay, we want to remember a couple of properties of fractions. So this would be one property of fractions. A plus b over c is a over c plus b over c. And another property would be, say, d times e over d times f. We can divide out the factors of d and we get e over f. We want to be very careful that, say, a plus b over b, something like this is not true. If we have a numerator, for instance, that's connected by, or with 2 terms connected by a plus or minus, we can't like cancel common terms, right? Or if we had something like a plus b over c plus b, if we thought something like this worked, again, something like that does not work. So we can divide out or cancel. I think it's technically divide out, but a lot of people just say cancel. When we have common factors, things multiplied on in the numerator or the denominator, but not when we have common terms. So we just have to be a little careful about that. Okay, so let's look at this first example. Maybe I'll zoom in a little bit, make it a little bigger on your screen. And of course, now my stuff I wrote over here isn't on the screen anymore. But for this first one, I see I can break this up as 15x squared over 5 plus 10x over 5, using my first property of fractions over here. And then for each of these terms, for the 15x squared over 5 and for the 10x over 5, each of them separately, I'm going to look and see if I can divide anything out. Is there a factor of 5 in the numerator? Sure, I could write 15 as 5 times 3. And I could write 10 as 5 times 2. I can divide out these 5s in my first fraction, just leaving me with 3x squared, and similarly in my second. Okay, so this monomial divided nicely into this quadratic, into this binomial. What if we were dividing 15x squared plus 10x by x? Same first step. So we break that one fraction into 2 with that same denominator under each fraction. And we ask in our first fraction, well, I have an x squared that has 2 factors of x in the numerator, and I have 1 factor of x in the denominator. So a lot of times we'll just kind of, as a shorthand, just cancel out that squared exponent with the x on the bottom, leaving me with 15x. And then the 10x over x, the x's cancel. So my monomial divides nicely into the binomial here as well. And if we look at something like this, where we have a slightly more complicated monomial, a number times a variable, same process. And here I notice that I can divide out the factor of 5. The 5 in the denominator goes away. The 5 in the 15 leaves a factor of 3. And I can also divide out the x with the x squared on the top. So this leaves me with 3x from my first fraction. And then doing the same for the second, the 5 in the denominator divides out with the 5 in, with the factor of 5 in the 10 and the numerator, leaving me with the factor of 2. Oh, I somehow switched the order of my pens. I don't know how I did that. Let me switch this back here. All right, there we go. I can divide out my x's as well, so I can get plus 2. So hopefully all of this looks pretty familiar. And even if we have something that looks a lot more complicated like this one down here, the procedure is still the same. We see a bunch of different powers on y. This might look a little more challenging at first, but it's really the same procedure. So we start by breaking them up into monomial over monomial fractions. And then I ask, okay, looking at my constants in the first fraction, 28 and 7. Is there any common factor? Yeah, the 7 in the denominator divides out with the factor of 7 in the 28, leaving me with the factor of 4. And for my variables, I have y squared in the denominator, y to the 4th in the numerator. I can either use a property of exponents, or I can subtract the exponents, or I can think of just dividing out 2 factors of y with 2 of the factors of y in the numerator, leaving me with 2 factors remaining. So I get 4y squared for my first fraction. And then from the second, the 7 divides out the factor of 7 in the 14, leaving me with 2. And then my y squared divides out 2 of my factors in the y cubed, leaving me with just a y. So even a more complicated looking problem like this one, really just the same procedure. How would this change if we had more terms in the numerator? If I had 3 terms or 4 terms, well, I would just have 3 or 4 fractions over here to go through. The procedure will be the same. I just have to do the same process a couple more times. So it wouldn't really become qualitatively any more difficult. It would just be a little bit longer of a problem. So if I add more terms to the numerator, it basically stays as the same problem. What if I add another term to the denominator? What if instead of dividing by a monomial, if I'm dividing by a polynomial, maybe we'll just start with a binomial that's linear. So something like x plus 2. Well, if we try to do something like what we did above, if we said, I wonder if this will work if I try the same procedure, it's not a bad idea. But I see I get something like x squared over x plus 2. I can't do something like divide out the x's here because I have this second term with the 2 in the denominator. So something like that is not going to work. So I see that this same strategy isn't going to work, the same strategy I used above. Note also that I cannot do something like I can't do something like that. I can't break up the denominator in the same way that I break up the numerator. That's just not how fractions work. So I can't really force this into a bunch of monomial over monomial problems. That was really what I did above. And I was really leveraging the fact that I had a monomial in the denominator. So that was really a crucial characteristic of these types of problems, is the denominator is a monomial. It doesn't much matter what the numerator is. If the denominator is a monomial, I can use this strategy up here. But that strategy doesn't generalize to a denominator that is a binomial or a larger polynomial. Okay, so what is my goal down here? Well, my goal is to get, I see I have a quadratic function over a linear. If I were to end up with being able to write this as something like, and I'm not saying that this is how this one turns out, but just hypothetically, if we were able to, we saw last time that we can multiply polynomials by foiling going this way. If I could undo that, if I could move in the opposite direction, I might be able to kind of unfoil, in a sense, or what we call factor, this numerator, this quadratic, into a product like this. And then I notice that I have a product of 2 things, and maybe I could divide them out. It would be super nice if this worked out, and that's really going to be the strategy we look at in chapter 7. It turns out that kind of going this direction is a little more complicated. So we're going to kind of devote a whole chapter to that, to talking about factoring and how to kind of unfoil a quadratic polynomial. So we're going to spend quite a bit of time looking at this kind of idea a bit later. But that would be a pretty good idea. That would be nice if we could do that. But the other problem is we're not always certain that we can actually do that, right? What if we ended up with a situation like this? We don't have any common factors to divide out anyway. So even if we were really good at doing this technique called factoring, there's no guarantee that we end up with common factors that we can divide out. So we have to come up with really a completely different approach. So let's come over here and let's ask ourselves, if I had, let's say, 173 over 12, and I wanted to simplify this, how would I do it? And these might be small enough numbers that you might be able to work through it in your head a little bit. But my goal here is to get a mixed number. So a number next to a fraction. So something like, 3 1/4 or something like that, which really just means 3 plus 1/4. So I'm looking for something like this. And again, if you can do this in your head, great. But if you imagine if there were bigger numbers, we would have to use long division. So I know long division is everybody's favorite subject, but so here's my long division setup. I have 173 divided by 12. So I put the numerator inside of my little long division symbol, my denominator outside. And then I ask, okay, well, how many times does 12 go into, well, does it go into 1? No, it doesn't. How many times does 12 go into 17? Does it go into that? Yeah, it does. 12 goes into 17 one time. 1 times 12 is 12. Put a minus in front. And then I subtract. 17 minus 12 is 5. And I bring down my next digit. 12 goes into 53. How many times? Well, 12 times 1 is 12, times 2 is 24, 36, 48. 4 times 12 is 48, leaving me with a remainder of 5. And this is what I get. I see that 173 over 12 is 14 and 5/12. So I have this way of working with just general numbers when I want to do long division. And I know that kind of what we had discussed before when we were multiplying polynomials, we had discussed that I could think of, for instance, 12 is 10 plus 2, or even more explicitly, 1 times 10 plus 2, and 173 as 1 times 100 plus 7 times 10 plus 3. This looks a lot like, 1x plus 2 or 1x squared plus 7x plus 3. It has the same kind of feel as dividing polynomials. Can I leverage what I know over here, doing long division with numbers, to solve a problem like this? So let's try it. So what did I do over here? I put my numerator on the inside of the long division bracket. I put my denominator on the outside. And then here I actually said, like, how many times does 12 go into 17? I'm going to take a slightly different approach here. Pretty similar idea, but I'm just going to look at the leading terms, at the terms with the highest powers of x. I'm going to ask, how many times does x go into x squared? Or in other words, what would I need to multiply x by to get x squared? X times what equals x squared? This, of course, has to be an x. Erase my little red brackets down there. Okay, so what did I do over here then? I said 12 goes into 17 one time. Then I did 1 times 12 and then subtracted that off. So if I follow the same pattern, if I do x times x plus 2 and write that down here. So what is x times x plus 2? I can use my distributive property, multiply this out to get x squared plus 2x. This is just scratch work up on top here. So x times x plus 2 is x squared plus 2x. So that was what I got multiplying through. And then I want to subtract that. So I see that this x squared plus 2x lines up nicely with the x squared plus 8x. I want to subtract it off, or what I'll do here, just to keep all of my signs nice, is I'll actually distribute my minus sign. So minus parentheses x squared plus 2x is minus x squared minus 2x. X squared minus x squared, they go away. So that's pretty nice. I no longer have x squared terms to deal with. And that was really why I asked how many times does x go into x squared, because that's really the term that I want to cancel off first. 8x minus 2x is 6x. And then what was the next thing we did? We brought down the next term, so to speak, the next number. So we bring down the plus 12. And then we repeat the process. So we go back and we ask, how many times does x go into 6x? Or in other words, x times what equals 6x? That has to be a 6. I multiply through. 6 times x plus 2 is 6x plus 12. I want to subtract off. And here I don't need to distribute the negative or anything. I can see that I have 6x plus 12 minus the exact same thing. So I end up with 0. There are no more terms to bring down. I don't have any other bits that I haven't brought down yet. I've got a remainder of 0. So this tells me that x squared plus 8x plus 12 over x plus 2 equals x plus 6. And if I wanted to really be pedantic, I could say plus 0 over x plus 2 like I did over here. But since I didn't really get a remainder, my remainder is just 0. I'll just leave that bit off. And we'll leave it here. So dividing x squared plus 8x plus 12 by x plus 2 just yields x plus 6. Now, one thing to kind of note is up above, we had a second degree polynomial over a constant that left us with a second degree polynomial. A constant is kind of like a 0th degree polynomial. It's like 5x to the 0, right? Because x to the 0 would just be 1. In my next example, I had a second degree polynomial over a linear monomial. A second degree over a first degree left me with a first degree polynomial. Again, second degree over first degree left me with first degree. Fourth degree over second left me with second. 4 minus 2 is 2. And even though this is not polynomial over monomial, that same pattern does carry through. Second degree over first degree leaves me with first degree. Quadratic over linear gives me a linear. So that's just something that's sometimes nice to kind of check. And that did work out nicely in this case. We see that the quadratic over the linear, second degree over first degree, leaves me with a first degree polynomial, as I would expect. Okay, so let's jump over to the worksheet for today. So I have 2 warm-up problems, so maybe take a couple minutes, go through these 2, and then try to work through this polynomial long division problem. Polynomial long division, this is a challenging topic, so if you don't get it right away, or if you're struggling a little bit, that's to be expected. This isn't an easy topic, and it does take a little bit of time. So just be careful with things like negative signs and making sure everything's distributed properly, and just take your time and go through it. So we'll take maybe, I think, about 7 minutes to work through these 3. And then as usual, a couple minutes in, I'll start writing out the answers to these 2. And then a few minutes after that, I'll kind of start working through the long division problem while you're working on it. And that way you can, if you get stuck somewhere, you can, maybe get unstuck by looking at my work, but try to do it on your own. And then if you get stuck, you can look up and see if what I've written is helpful. But we'll take about 7 minutes for these 3 problems. The first 2 should go pretty quickly, and then the long division problem will take a little longer. All right, so I will touch base back with you guys in about 7 minutes. Okay, so it's about 7 minutes now. So the two monomial problems I think are pretty straightforward. We just do the same process, split up into two fractions, and then divide out common factors. So I don't think anything super interesting or novel there. Again, this was just kind of a review just to get us back in the swing of things after spring break. So let's go carefully through the long division problem. So here we had x squared minus 4x plus 4. That goes inside of the long division bracket. That's the numerator. Divided by x minus 2, the denominator, goes outside of the bracket. And again, I just look at my leading terms or my highest degree terms at each step. So I ask, how many times does x go into x squared? Or another way of saying that is x times what equals x squared? Well, of course, x times x equals x squared. So that gives me my first term in my answer. I then multiply down x times x minus 2. I distribute and I get x squared minus 2x. And I have to subtract that off. So I have minus x squared minus 2x. And again, I would probably distribute this negative and make this a minus x squared plus 2x. And I see that now I have x squared minus x squared. The x squareds go away. So I now have one fewer term to deal with. That's good. Negative 4x plus 2x is minus 2x. I have my minus 2x down here, and then I bring down the 4 to get my next binomial, minus 2x plus 4. And I repeat the process. How many times does x go into minus 2x? Or in other words, x times what gives me minus 2x? That's a negative 2. So negative 2 is the next term, or minus 2 is that next term in the answer. Negative 2 times x minus 2 gives me negative 2x plus 4. Make sure to distribute that negative 2x plus 4. And we're subtracting that here. And of course, I have one thing minus the same thing gives me a remainder of 0. So my claim then is that x squared minus 4x plus 4 over x minus 2 equals x minus 2. Now that was quite a bit of work that we did. We could have made a mistake somewhere. Super easy to miss distributing a negative sign or something. So we can check our work. We note that with a fraction in general, if a over b equals c, that means that a equals c times b. So we can check division with multiplication, and we could do that here. If it's indeed true that x squared minus 4x plus 4 over x minus 2 does equal x minus 2, I should be able to multiply both sides by this x minus 2, and that should still be a correct equation. In other words, it should be the case that x squared minus 4x plus 4 equals x minus 2, say this x minus 2, times x minus 2 coming from that denominator. So let's check that. So what is x minus 2 times x minus 2, this perfect square binomial? Well, if we FOIL it, the first give me x squared. The outsides give me minus 2x. The insides give me another minus 2x, so that's minus 4x. Then the last give me minus 2 times minus 2, or plus 4. And that is exactly what we were looking for. If I can draw my arrow. So we have confirmed that this answer that we got is correct. And that's also something we could do here. To check our answer, let's multiply x plus 6 by x plus 2 and make sure we get x squared plus 8x plus 12. Multiplying the first give me x squared. The outsides plus 2x, insides plus 6x, and last plus 12. 2x plus 6x is 8x. So that looks good. X squared plus 8x plus 12 is our numerator up here. So we have checked that x plus 6 is the answer up here. Right, a lot of times with these, especially with the more complicated topics and the ones that require more calculation, just more places to make a mistake, really remembering how you can check your work at the end is really beneficial. If you drop a negative sign somewhere, if I, had forgotten to distribute my negative here, and this was still a plus 2x, and I had ended up with like a 10x here instead of a 6x, I wouldn't have known just looking at the answer that I did something wrong until I went to do the check, and then the multiplication didn't turn out correctly. Okay, so let's look at another example. 3x squared minus 10x plus 30 all over x minus 3. Same procedure. We have our numerator goes inside of the long division bracket. And our denominator outside. And we start with the same question. Looking at our highest degree terms, how many times does x go into 3x squared? Or in other words, x times what equals 3x squared? Well, to get the constant right, I need a 3. And to get the variable power right, I need another factor of x. I multiply through 3x times x minus 3. 3x times x is 3x squared. And 3x times minus 3 is minus 9x. And I want to subtract off that whole thing. And again, I want to really think about distributing that negative sign through. So that's a minus 3x squared, and then minus a negative is plus 9x. My 3x squareds go away. So again, I've in this first step gets rid of one of my terms that I have to deal with. My x's, I have minus 10x plus 9x is minus x. And then plus 30. So that finishes that first step. And now I just repeat the process dealing with a polynomial that is 1 degree lower. Instead of a second degree, I now have a first degree polynomial. X goes into negative x how many times, or x times what? Equals negative x. Of course, that's a negative 1. So I put a minus 1 up there. I multiply through. Negative 1 times x minus 3 is negative x plus 3. And again, I'm subtracting this. But again, I want to distribute my negative sign just so that I am less likely to make a mistake. Negative times negative x is positive x. And negative of positive 3 is negative 3. And again, my x's go away. Minus x plus x, they go away. 30 minus 3 is 27. I don't have anything else to bring down. Everything is taken care of up here. If I tried to ask a question like how many times does x go into 27, or like x times what equals 27, there's no real good answer here. I mean, I guess I could say 27 over x, but that's kind of a, that's not really what I'm looking for. I'm looking for a polynomial answer, x to positive powers. Well, it turns out that this doesn't divide perfectly, right? The same way that, maybe 12 over 3 gets me a whole number answer of 4, but 10 over 3 gets me a whole number part with a remainder. So this previous example and the one that we did in the worksheet divided out nicely. It was a little more like the 12 over 3 equals 4 kind of idea, where I didn't get a remainder. But this example is more like the 10 over 3 example where I do get a remainder. So my kind of whole number part, or my whole polynomial part of the answer, is 3x minus 1. But then I have a remainder bit, plus 27 over x minus 3. The same way that I did up here, right? I have a whole number bit plus the remainder divided by the original denominator. The same pattern applies to these whole number division problems and to these polynomial division problems. So I have 3x minus 1, that's like my whole polynomial part, plus the fractional part that's left over, the part dealing with the remainder. So plus 27 divided by x minus 3. Now, how do I know that this is a remainder? And how did I know that, say, negative x plus 30 was not a remainder? Well, if I had thought that I could, say, stop here and come down and write something like 3x plus negative x plus 30 over x minus 3. If I thought I could maybe say something like that, this isn't fully simplified because I have a first degree over a first degree. Right? I should still be able to divide something out here. I only call it a remainder when I have something like this, where I have a constant or a 0th degree over a first degree. Only when the degree of the numerator is smaller than the degree of the denominator, that's when it's a remainder. Because at this point, I cannot divide anything else out. Or a more practical way of looking at it is when I ask the question, x times what equals negative x, I can answer that, -1. When I ask the question, x times what equals 27, I don't have a good answer to that, right? I mean, I guess you could say 27 over x, but again, we're looking for answers that look like monomials. So I don't have a nice monomial answer to this question. So that's where I stop. And this is about the best I can do as far as simplifying goes. I did break off a polynomial piece, but I was stuck with this bit at the end here. Now, can I check my work? Let me see if I can get a little more room. Can I check my work? What I would like to do is multiply through by the denominator and see if I get an equality that I'm happy with. So I'd like to multiply x minus 3 by 3x minus 1 plus 27 over x minus 3. And I'm hoping that I get this numerator. I can distribute this to each of these three terms. Now this 27 over x minus 3 isn't really a polynomial term, but the distributive property still works. So I have x minus 3 times 3x plus x minus 3 times negative 1 plus x minus 3 times 27 over x minus 3. Or I can write that 27 over x minus 3 this way. And I see that these x minus 3s are just common factors in that last term. They just cancel. They just divide out. So this last term just becomes a plus 27. For each of my first two terms, I'll distribute again, being careful with my negatives. So I have 3x times x is 3x squared. 3x times negative 3 is minus 9x. My minus 1 distributes, minus x plus 3 plus 27. And now I combine like terms, 3x squared, that doesn't have any other x squared terms to combine with. Minus 9x minus x is minus 10x. Plus 3 plus 27 plus 30. And that is 3x squared minus 10x plus 30. That is the numerator I started with. So I've checked that the answer I have up here is correct. So again, lots of calculations, lots of little, what I call kind of bookkeeping, just like keeping all the negatives straight, keeping all of the, the x squared and the x terms and so on in line. And so all of these just little details, these little bookkeeping issues, they're really the biggest thing with this. Once you get the strategy down, and if you forget the strategy, just go through long division with a couple of numbers and remind yourself of the strategy. Once you get the strategy down, it's not too bad. It's just repeating the process over and over. But it's really all these little details that can trip you up. So just be careful with all of those. And then, of course, check your work at the end because it's so easy to get one of those little details wrong. Okay, so let's jump down to this problem. So why don't you take about, say, 5 or 6 minutes to work through this one. Again, go through carefully, work through it, get your answer. And then once you get your answer, when you get your answer, check your answer by multiplying. So multiply your answer by 2x plus 4, distribute everything out carefully, and make sure that you get the numerator at the end. So that way you verified your answer. So take maybe about 6 minutes or so to go through, get an answer, and then check it at the end. Okay, so let's work through the answer. So we set up the problem. The numerator, 6x squared minus 8x plus 3, goes inside the long division symbol, and the denominator, 2x plus 4, goes outside. And we start by asking, how many times does 2x go into 6x squared, or 2x times what equals 6x squared? To get our constant right, we need to multiply by 3, and to get our variable powers right, we need to multiply by x. So we get 3x as our first term in the answer. We multiply through 3x times 2x plus 4. I distribute, that gives me, and just to be clear, this whole 3x I'm distributing through, right? That gives me 6x squared plus 12x. So I do minus 6x squared plus 12x, but then I distribute the minus, so that makes a minus 6x squared minus 12x. My 6x squareds go away. Negative 8x minus 12x is negative 20x. And then I bring down my next term, which here is a plus 3. And I repeat the process. 2x times what gives me negative 20x? That's a negative 10. Negative 10 times 2x plus 4 gives me negative 20x minus 40. But I'm subtracting that. So I'd have minus parentheses negative 20x minus 40. Distributing the minus gives me a plus 20x plus 40. And again, if you want to write this out in a couple of steps, that's not a problem at all. But here I just combine those couple of steps into one. I see my minus 20x plus 20x. The x term goes away now. But my constant term doesn't go away. I have plus 3 plus 40 gives me 43. So I might say that my quotient, you might remember these terms from an earlier course. My quotient is 3x minus 10, and my remainder is 43. I might say it that way. Or the way that I would write it out algebraically is like this. I would say this fraction equals 3x minus 10 plus, so again, my quotient plus my remainder divided by the original denominator. So 3x minus 10 plus 43 over 2x plus 4. Then lastly, I did a bunch of work here, a lot of negative signs floating around. I should check my work. So I want to check that if I multiply both sides of this equation by 2x plus 4, I should get, if I can select it, I should get just my numerator, 6x squared minus 8x plus 3. So let's check that. I'm going to multiply this whole 2x plus 4 into each of these 3 terms. And I'll keep that minus 10 kind of separated off by itself, so I don't forget to distribute the minus sign. In my last term, this is always the kind of confusing term, but I realized that when I'm multiplying by the original denominator, that just ends up dividing out with that remainder term. So it looks a little scary at first, but it just divides out. Everything's okay with that last term. And this is a 3x that I'm going to distribute into here. So this gives me 6x squared, 3x times 2x, plus 3x times 4, so plus 12x. I'm going to distribute my negative 10 into each of those two terms. So I get negative 20x minus 40 plus 43. Okay. And now I combine like terms, I get 6x squared plus 12x minus 20x is minus 8x. minus 40 plus 43 is plus 3. And this is exactly my numerator. So when I multiply through by the denominator, multiply both sides by the denominator, on the right-hand side, I get a big mess, but I simplify all of that down, and that turns out to be exactly what I would expect. So I've checked that, I didn't drop a negative or do anything like that during all of this work over here. Any questions on any of these so far? Okay, so let's work through one more problem. And this problem is a little bit different. It looks very similar to the previous ones. There are 3 terms over 2 terms, so a 3-term polynomial over a binomial. My denominator is a linear. Looks very similar. There's one thing that's a little different, though. My numerator here is a cubic. 2y cubed minus 4y minus 42. So it has a third power. It's a third-degree polynomial instead of a second like we've been dealing with. Up here, again, I had a second degree over first degree. I expect to get a linear. As a result. Where did I even write my, here, there's my solution. And I get something that basically looks like a linear. The highest degree that I see on x is a first power. Third degree over first degree, I expect to get something with a second power, a quadratic, as the answer. There's one more little wrench in the works, though, and that's that I'm completely missing my y squared term. So let's see how that affects things. If I set up my my long division symbol, and under it I put my numerator, 2y cubed minus 4y minus 42 over y minus 3. And let's kind of proceed forward. So the first step is to look at my leading terms. Y goes into 2y cubed how many times, or what do I need to multiply y by to get 2y cubed? That's got to be 2y squared. 2y squared times y gives me 2y cubed. So 2y squared times y gives me 2y cubed. And 2y squared times negative 3 gives me negative 6y squared. Now here I have something a little funny that happened. I have a y squared term. It doesn't really line up so nicely with the term above it. Should I do minus 4y minus 6y squared and then bring down the minus 42, or how should I handle this? Well, what we want to do in this case, we want to force a y squared term up here. So 2y cubed plus what y squared minus 4y minus 42. Well, if I don't want to change anything, that's got to be a plus 0y squared. The same way that if I had, 3 times 100 plus 4 or something like this, I wouldn't write this as, 3, 4. I wouldn't write it that way. I would write it as 304. In other words, I would explicitly know the 3 lots of 100 plus 0 lots of 10 plus 4. Right. So many of these things that we're doing with polynomials that seem very strange and abstract and confusing, you can just reframe them in terms of just regular old numbers, and the stuff works the same way. So why am I forcing this 0y squared in here? Well, because I kind of need a placeholder there, just like 34 isn't the same number as 304. We can get away with not explicitly writing this 0y squared sometimes because we have a little bit more algebraic symbols and so on going on here. But when we're really working with these polynomials, it's always good to just remember that there's kind of hiding in the background a 0y² if we need it as a placeholder. And here I think it will serve us well to use it as a placeholder. So we'll do that. So now and I need to write down the rest of my polynomial, minus 4y minus 42. Now it looks like we're, and 2y² times y is 2y³. 2y² times -3 is -6y². And now I want to subtract this whole thing, which means I make this a minus 2y³ plus 6y². And now I have a 6y² minus 4y. Okay, so now what do I do? Well, I repeat the process, right? How many times does y go into 6y², or y times what gives me 6y²? That's a 6y. 6y times y gives me 6y². 6y times -3 gives me -18y. Again, I want to subtract this whole thing. I distribute that negative. My y² terms go away. Minus 4y plus 18y is plus 14y. I guess I don't need the plus there. Just 14y. And then I bring down my next term. I have another term to bring down, so I do. And I also note that y goes into 14y 14 times, so I'm not done yet. Right, so minus 42. As an aside, when I bring down these terms, I'm, as usual, being very careful to bring my negative signs along with the terms when there is a negative sign there. And I repeat the process one more time. Y goes into 14y how many times? 14. 14 times y is 14y. 14 times -3 is -42. I'm subtracting this, and here, nicely enough, I do get a remainder of 0. So y minus 3 does divide nicely into 2y³ minus 4y minus 42. And this quotient is 2y² plus 6y plus 14. I have a third degree polynomial over a first degree. I expect to get a second degree as the answer. That's what I got. So that's kind of one reasonability check. That seems in line with what I'd expect. But let's check the details. Let's multiply through and just make sure everything checks out. And I think if I try to squeeze this in on the left side here, I'm not going to have enough room. So I'm going to come down to the bottom and then multiply out. So I want to do y minus 3 times 2y² plus 6y plus 14. And my question is, does that end up as 2y³ minus 4y minus 42? If my equals up here is correct, if I've done my work correctly, then when I multiply through, I should get the product of y minus 3 with the right-hand side equaling just the numerator on the left. So let's check that. Distributing each of these three terms. And then distributing again. 3 more times. And nicely enough, we have a minus 6y squared plus 6y squared. Those cancel. I have a 2y cubed that doesn't have any other like terms. Minus 18y plus 14y gives me a minus 4y. And then a minus 42 doesn't have any other like terms. And that's exactly what I expected. So I've now checked my answer and verified it's correct by multiplying through. So the key new idea here is if we're missing kind of a middle term, so to speak, if we have a cubic and we're missing the quadratic term, or if we were missing the linear term, or if we have a quadratic and we're missing the linear term, a second degree polynomial and we're missing the first degree term, we want to put it in here as a placeholder. We want to make sure that we account for that over here so that it just keeps everything kind of nicely lined up, keeps everything organized, and we can just go through this procedure until we end up with either zero remainder or, in this case, or a constant remainder. Okay, so let's work through this last one here. 27y cubed minus 125 over 3y minus 5. And because this one is a little bit longer, and again, you'll have to put in some of those placeholders, let's take about 7 minutes for this. So go through, get the answer, and then also check your answer at the end. And then in 7 minutes, we'll come back and work through it together.
I have a quick question whenever you have a moment.
Yeah, sure.
So I see that you added that zero y squared, like how you were talking about to kind of like
Mhm.
force having those together. Is there any way that we would be able to like tell that we have to do that before we start the problem?
Yeah, sure. So because we have a cubic here and we see that there's no y squared or y term, it's not like a, 27y cubed, like minus 3y squared plus 2y minus 125, right?
Hmm.
So we know that we're missing the y squared term and we're missing the y term. We don't have to do like a fourth power or anything because, that's a higher degree than the y cubed. But because we have a third degree up here, we'd expect to see a second degree term, a first degree term, and a constant term. Here we don't see the second degree term or the first degree term explicitly anywhere.
Hmm.
So that's where we just put in each of those terms here. So
Okay,
oh, all of the terms that are lower degree than the highest degree term we see should appear in here. And if they don't naturally appear, we just put them in with a coefficient of 0.
okay.
Yeah.
Okay, yeah, because I was trying to like put them in while I was doing the work, and that's why I got confused. So I just didn't know if there was like a way. But yes, thank you for clarifying that.
Yeah, it's definitely best to put them in at the beginning. And so when I kind of first started that last one, I just wanted to show why if we didn't put them in, everything gets kind of lined up a little wonky and you still might be able to like force it to work, but it's I think it's pretty difficult to figure out what's going on in that case. Like here we really kind of leveraged bringing down the 0y, for instance. Um,
Yeah, without having it there initially, I just straight up got lost. So that's why I was like, is there any other
exactly.
way?
Yeah, exactly. And so we're always on the lookout for like all of the different degrees of terms represented, and if not, we just make sure to add in a placeholder for those degrees that are missing. Yeah, great question though. Okay, yeah. So working through the answer, again, we put our numerator underneath the long division symbol, and then we add in the 0y squared and the 0y as placeholders. So we have 3y minus 5. 3y goes into 27y cubed. I need a factor of 9 so that 3 times 9 is 27. And I need a factor of y squared so that y times y squared is y cubed. So that gives me 9y squared as the first term in my answer. I multiply through 9y squared times 3y is 27y cubed. 9y squared times negative 5 is minus 45y squared. And then remember that I want to subtract that off. So I've switched each of those signs. So 27y cubed minus 45y squared, but that all has a minus in front of the whole thing. That minus distributes through and just changes each of those signs to a negative 27y cubed and a positive 45y squared. My y cubed terms go away. And I have 0y squared plus 45y squared just gives me 45y squared. I bring down the next term. In this case, it's 0y, but I still bring it down and I can write it there. And then I repeat the process. So again, before I asked how many times does 3y go into 27y cubed, now I just ask how many times does 3y go into 45y squared. To make the constants turn out right, 3 times what is 45? That's got to be 15. Y times what is y squared? That's got to be y to the first power. So 15y has to be my next term in the answer. And then I multiply through 15y times 3y gives me 45y squared. 15y times negative 5 gives me minus 75y. And again, remember that this negative in front distributes through and flips all of those signs. So the plus 45y squared gets its sign flipped to a negative 45y squared, and the minus 75y gets its sign flipped to a plus 75y. My 45y squareds go away, so I've gotten rid of my second degree terms now. I've gotten rid of one more piece. 0y plus 75y gives me 75y. I bring down the next term, the minus 125, and repeat the process. 3y times what is 75y? That is 25. 25 times 3y is 75y. 25 times negative 5 is negative 125 with a minus sign in front. And I see I have a binomial minus the exact same binomial. So that gives me a remainder of 0. This binomial divides evenly into that numerator. So 27y cubed minus 125 over 3y minus 5 should equal 9y squared plus 15y plus 25 with no remainder, with no fractional term. And then we want to check our work. So we multiply through by the denominator. So if my statement up here is correct, then when I multiply through by 3y minus 5, on the right-hand side, I have 3y minus 5 times 9y squared plus 15y plus 25. And that should equal just the numerator on the left-hand side. So this all should equal 27y cubed, y cubed minus 125. And I went through a little bit of the work already down here. So I distributed the 3y minus 5 to each of these three terms. I then did three more distributive properties. 9y squared times 3y is 27y cubed. 9y squared times minus 5 is minus 45y squared, and so on. And I see that my y squared terms perfectly cancel. My y terms perfectly cancel. And then I'm left with just the y cubed term, 27y cubed, and the constant term minus 125. And that is exactly what I wanted to end up with. So I've checked my answer. Again, always a good idea to check your answer on these. It's so easy to just miss a negative or subtract a little bit wrong, or do a multiplication a little wonky and end up with the wrong answer. So always a good idea to check your work. And of course, if I came down here and I, whatever, got 27y cubed plus 12y minus 125, and that didn't work or something, I would go back here and I would just double check all of my steps from my long division. And I'd probably find at some point I made some little error. I'd erase everything from that point forward and then just go back and rework it. This isn't the kind of thing where if you make a small error in the middle, you can kind of just easily trace that error through. If you make a small error, you just kind of have to rewind up to that point and then proceed back from there. But yeah, it would be a shame to kind of do all of this work and then, have made some small error and have your answer completely incorrect. That's why it's a good idea to just check your work at the end. It does take a few minutes. It's not, a super quick check, but I think it's worth it, especially given how much work we do to get the answer. All right, are there any questions on polynomial long division? So I know this is a challenging topic. It's one of those topics where the first couple of times you go through it, it's just like you're like barely holding on and figuring out what comes next. Maybe for the first 3 or 4 times that you go through a problem like this, the next 3 or 4 or 5 times are, challenging, but a little better. And, the next 3, 4 or 5 times go a little more smoothly. And, it's one of those things that as you go through it several times and you drill it a little bit, it gets easier and easier. And if you're stuck somewhere, I think it's always a good idea with polynomials just to keep an example kind of like this in the back of your mind, right? That that polynomials work a lot like numbers when you think of numbers in this sense, but like whole numbers, positive integers. Polynomials work a lot like positive integers when you think of them like this, or to be even more explicit about this, this is like 1 times 10 squared plus 7 times 10 to the first plus 3, right? I mean, this looks a heck of a lot like 1 times x squared plus 7x plus 3. So polynomials work a lot like numbers, so we can always refer back to these similar procedures we did just in arithmetic, just working with numbers, and we can think in terms of things like powers of 10 and ask, okay, how did all of this work back then? And how does that procedure translate over to polynomials?